Welcome to a video on getting started with applications of linear programming. In this video, we're going to focus on setting up the problem, which includes setting up the objective function and the constraints. Let's get started. In general, when you solve applications of linear programming, you want to start by defining the variables, then write the equation of the objective function and identify the goal. This will be whether you want to maximize or minimize the objective function. Then write each constraint as an inequality. Once you have your objective function and constraints written, then it's time to graph the feasible region. Then you'll want to identify the corners of the feasible region and evaluate the objective function at each corner to determine the solution. In this video, I'm going to focus on the first 3 steps, which is just how to set up the problem. In the video description, you'll find links to different videos where I go into greater detail on steps 4, 5, and 6. Before we get started, let's take a look at some pro tips. The objective function is going to be an equation. This is the function you want to maximize or minimize. Look for the goal of the problem to help determine the objective function. Once you have your objective function, the variables will be used to write the constraints. The constraints are the inequalities. So when you're reading the problem, look for phrases that express inequality. Here are some of the most commonly used phrases, but this list is not exhaustive. For phrases that imply less than or equal to, look for phrases in the problem such as at most, maximum, not to exceed, no more than, or not above. The phrase maximum can often trip up students. You can maximize the objective function, but the word maximum may also be used in terms of a constraint. You might have a maximum amount of materials to use to produce an item. You can also look for phrases that imply greater than or equal to. These would be phrases such as at least, minimum, exceeds, no less than, and not below. And like I said, these are probably the most common phrases, but this list by no means is exhaustive. Let's take a look at our first example. This is a manufacturing problem. A factory manufactures 2 types of gadgets, regular and premium. Each gadget requires the use of 2 operations, assembly and finishing, and there are at most 12 hours available for each operation. A regular gadget requires 1 hour of assembly and 2 hours of finishing, while a premium gadget requires 2 hours of assembly and 1 hour of finishing. Due to other restrictions, the company can make at most 7 gadgets a day. If a profit of $20 is realized for each regular gadget and $30 for a premium gadget, how many of each should be manufactured to maximize profit? Now that we've read the problem, you might be wondering, where should I start? A good starting point is to look for the goal of the problem. This is your objective. Then try to determine what the goal depends on. These are usually going to be your variables. Let's go back to the problem and look for the goal, and then look what the goal depends on. To find our objective, in this problem, we need to focus on that last sentence. At the very bottom, we can see that we are asked to maximize profit. This is our goal. This is going to be our objective in this linear programming problem. But we also need to determine what the profit for this company depends on. And in that same sentence, it says that it depends on the number of regular gadgets sold and the number of premium gadgets sold. If our profit depends on how many regular and premium gadgets are sold, the profit is going to be our objective, and the variables are going to be the regular and premium gadgets. Remember, your objective depends on the variables. Now that we've identified the objective and our variables, it's time to get organized. In this video, I'm going to show you how you can use a table to help organize a lot of information. You do not have to use a table to organize your information. However, this table method extends nicely if you're going to use the Excel solver down the road. Not all courses use the Excel solver. However, you can use this method to set up all linear programming problems. Here's the table I'm going to use for this factory problem. Remember, our goal is to maximize profit. Before I jump right into setting up this table, let me explain the strategy behind it, because the strategy will work toward all linear programming problems. Down the left-hand side, you want to write your objective function and your constraints. In this case, I'll usually write one constraint per row. So we're going to have our objective function and our constraint down the left side column. The next columns will be reserved for variables. You want to reserve one column for each variable. We know we're going to have two variables in this problem, so we're going to need two columns set aside. Then it's always a good idea to reserve one column for the total. Most linear programming problems will have you adding things together. And the very last column of my table will be where I write my equations and inequalities. This is the strategy I always use to set up linear programming problems. Let me show you how I'll set it up for this problem now. Since our objective function is the profit, I'm going to have the profit be my first row in this table. The first two columns will be reserved for the variable, so I'll have one column for my regular gadgets and the second column for premium gadgets, and then one column for the total and another for the equation or the inequality. The last three rows are going to be reserved for the constraints. In the middle of the table, we're going to write information that relates the variables to the objective function and the constraints. This is so important because we use this information to build the objective function, which is an equation, and the constraints, which are inequalities. Now that we've identified the variables and the objective, let's get more specific. Specifically, we need to define the variables. This means literally you need to pick a letter to represent for each quantity. Oftentimes students will tell me that they have the hardest time deciding what the variables in the problem are. Remember, the objective function depends on the variables. We're going to build the objective function using the variables. Once again, let's go back to our problem statement and look for more specific information that relates the variables and the objective function. We know our objective is to maximize profit, so let's just use P to represent profit. That will be measured in dollars. Let's use X to represent the number of regular gadgets sold and Y to represent the number of premium gadgets sold. Let's also take specific note of how these variables are related to the profit function. In the last sentence, it tells us that a profit of $20 is realized for each regular gadget and $30 is realized for each premium gadget. Let's go back to our table and fill this information out, and I'll show you how you can use the table to help build the objective function. We know this company earns $20 profit for each regular gadget sold and $30 profit for each premium gadget sold. We used X to represent the number of regular gadgets sold and Y to represent the number of premium gadgets sold. This is enough information to build our objective function. Remember, profit is going to be our unit profit times the number of items sold. Now we can go ahead and figure out the total profit earned for this company. This would be 20x plus 30y. Putting it all together, our profit function would be P equals 20x plus 30y. That's our objective function. That's the function we're going to maximize when we solve this problem. Now we're ready to look for the constraints. Constraints are limiting factors. Remember, these are going to be inequalities, so look for key phrases in the problem that suggest an inequality. Let's go back to the problem statement. This time we're looking for constraints. The first constraint can be found in the second sentence. It says, each gadget requires the use of two operations, assembly and finishing. There are at most 12 hours available for each operation. That phrase "at most" was one of our key phrases that suggests an inequality. At most is usually represented by less than or equal to. So now we know that our last two rows are going to be for assembly time and finishing time. Those are our constraints. And this company has at most 12 hours for assembly and finishing time. I've written that in the last column because at most suggests the inequality. Now we want to go back to the problem to determine how our assembly and finishing related to regular and premium gadgets. It says that a regular gadget requires 1 hour of assembly and 2 hours for finishing, while a premium gadget requires 2 hours of assembly and 1 hour of finishing. So regular gadgets need 1 hour of assembly time and 2 hours of finishing time. Premium gadgets need 2 hours of assembly time and 1 hour of finishing time. Let's calculate our total for each. So our total assembly time would be 1 times X plus 2 times Y. Our total assembly time can take at most 12 hours. So we can now write this as an inequality. 1x plus 2y is going to be less than or equal to 12. Similarly, for finishing time, that will be 2x plus 1y. And we know finishing time is at most 12 hours. So we can build our inequality 2x plus 1y is less than or equal to 12. Let's keep reading the problem to make sure we've captured all of our constraints. That fourth sentence says, due to other regulations, the company can make at most 7 gadgets a day. There's that key phrase, at most, again. That also tips me off that this has got to be a constraint. So the company can make at most 7 gadgets a day. That relates to the total number of items. The company can make at most 7 items per day. Let's finish this out and write our last inequality. So the total number of items made would just be X plus Y. And if they can make at most 7 items per day, our inequality would be X plus Y is less than or equal to 7. Now we have our objective function and 3 constraints. And actually, there are 2 more final constraints. X has got to be greater than or equal to 0, and Y has got to be greater than or equal to 0. The variables must be positive. That's really true for all linear programming problems. These are referred to as trivial constraints because they tend to be implied that the variables have to be positive. So putting this all together, for our manufacturing problem, where our goal is to maximize the profit, we need to maximize the function P is equal to 20x plus 30y, subject to the following constraints. X plus y is less than or equal to 7, x plus 2y is less than or equal to 12, 2x plus y is less than or equal to 12, x is greater than or equal to 0, and y is greater than or equal to 0. That completes the first 3 steps. To finish this problem, you would need to graph the feasible region, identify the corners, and then evaluate each function at the corner to determine the solution. In the description for this video, you'll find a link to a separate video where I spend time setting up the feasible region, identifying the corners, and evaluating the objective function at each of these corners for this specific problem. So if you'd like to see specific details on these last 3 steps, please see the video description. Essentially, what you would want to do is you would take your constraints and set up the feasible region, which looks like this polygon here. Then you would identify the 5 corners, 0, 0, 6, 0, 5, 2, 2, 5, and 0, 6. You take those corners and evaluate the objective function, which is our function for profit here, P equals 20x plus 30y, and you evaluate that function at each of those 5 coordinate points. You use the function values to determine your maximum value. In this case, it looks like we have a maximum at the coordinate 0.25 and the maximum profit is 190. So for this problem, our solution is the 0.25. That's where profit is maximized. Maximum profit is $190. And to produce the maximum profit, this company should make 2 regular gadgets and 5 premium gadgets. Now let's look at a second example. Our second problem says, a health food business would like to create a high potassium blend of dried fruit in the form of a box of 10 fruit bars. It decides to use dried apricots, which have 407 milligrams of potassium per serving, and dried dates, which have 271 milligrams of potassium per serving. The company can purchase its fruit in bulk for a reasonable price. Dried apricots cost $9.99 per pound, about 3 servings, and dried dates cost $7.99 per pound, about 4 servings. The company would like the box of bars to have at least the recommended daily potassium intake of about 4,700 milligrams and contain at least 1 serving of each fruit. In order to minimize costs, how many servings of each dried fruit should go into the box of bars? Looking down in the last sentence, we see that our goal is to minimize cost. In that same sentence, we know that we want to find the number of servings of each dried fruit. This problem says that the bars will be made of dried apricots and dried dates. So we know we want to minimize costs, so let's let C represent the cost of the mixture. Let's let X represent the number of servings of apricots and Y represent the number of servings of dates. Now that we know what the goal is and we've defined our variables, let's try and see how all of these variables are related so we can build our objective function. Toward the middle of this paragraph, we see that dried apricots cost $9.99 per pound for about 3 servings, and dried dates cost $7.99 per pound for about 4 servings. This will help us relate the cost, which is what we're trying to minimize, to our variables, which are the number of servings of apricots and dates. Let's head over to our table and start organizing our information. Our objective is to minimize the cost, so that's going to be the first row in our table. And our 2 variables are going to be the number of servings of dried apricots and dried dates. We used X to represent the number of servings of apricots and Y to represent the number of servings of dates. The problem also told us that apricots cost $9.99 per pound for 3 servings, and dates cost $7.99 per pound for 4 servings. Now, before we go on, something interesting is happening here. We were asked to find the number of servings for apricots and dates, but the prices were given per pound, and we know that a pound is more than a single serving. For apricots, a pound is about 3 servings, and for dates, a pound is about 4 servings. So we have to convert these costs for both the apricots and the dates to a price per serving. So if I take $9.99 and I divide it by 3, I would get that the apricots are $3.33 per serving. As for the dates, if we take $7.99 and divide it by 4, we would get a cost of about $2 per serving. We have to make sure that our units are lining up. You cannot use the cost per pound if you're measuring X by the number of servings. So now that we've fixed our units, let's figure out the total cost would be $3.33 times the number of servings of apricots, which is X, plus $2 times Y, which is the number of servings of dates. So our objective function is going to be C equals $3.33 X plus $2 times Y. Now that we have our objective function, let's go back to the problem and look for our constraints. When you're looking for the constraints, you're looking for those limiting factors. You can also try to see if you can find any of those phrases that represent inequalities. In the second to last sentence, we see our constraints or our limiting factors. The company would like the box of bars to have at least the recommended daily potassium intake of about 4,700 milligrams and contain at least 1 serving of each fruit. So our constraints are going to be the amount of potassium and the number of servings of each fruit. Since we know potassium is one of our constraints, we need to backtrack further up in the problem. In the second sentence, it says the business decided to use dried apricots, which have 407 milligrams of potassium per serving, and dried dates, which have 271 milligrams of potassium per serving. Let's use the table to formulate our constraints. One of the constraints was potassium, and we're told that apricots have 407 milligrams per serving and dates have 271 milligrams per serving, for a total of 407 milligrams times the number of servings, which would be X, plus 271 times Y. We're also told that the amount of potassium must be at least 4,700 milligrams. This means that the total amount of potassium, which was 407X plus 271Y, must be at least, which is greater than or equal to 4,700. We're also told that there should be at least 1 serving of each fruit. This means that X has to be greater than or equal to 1 and Y needs to be greater than or equal to 1. So on this middle row where the number of servings are, we don't need to use the total box, and that's okay. At least 1 serving each means that X has to be greater than or equal to 1 and Y has to be greater than or equal to 1. We don't need to add these together here. So for the dried fruit mixture problem where we're trying to minimize cost, we want to minimize the function C equals $3.33 times X plus $2 times Y, subject to the constraints 407X plus 271Y is greater than or equal to 4,700. X has got to be greater than or equal to 1, and Y has got to be greater than or equal to 1. Now that we've set up this problem, to finish, all you would need to do would be to graph the feasible region, identify the corners, and then evaluate the objective function at each corner so you can determine the solution. If you want to see the specific details on how to complete these last 3 steps, please see the video linked in the description below. But essentially, the next thing you would do is you would take your constraints and set up the feasible region. You would find your 2 corner points, which would be 1, 15.8, and 10.91. Then you would take those corner points and evaluate the cost function at those 2 points. You would then use the function values to determine the minimum. For this problem, our minimum occurs at the point 1, 15.8, and the minimum cost would be $34.93. So our solution would be the coordinate point 1, 15.8, which tells us that the company can minimize cost by using 1 serving of apricots and 15.8 servings of dried dates. This answer tells us that cost is minimized when the bars are pretty much all dried dates. However, because they have the added constraint that there must be 1 serving of each fruit, they can say that there is definitely 1 serving of apricots in the bars. That's it for this video. Thanks for watching.